pleased to present an oral report that shows various demonstrations of our ability to synthesize information, construct coherent narratives, and communicate ideas effectively. The content of our oral report is about an experiment entitled The Laws of Chemical Reactions, which we are going to embark on a journey of exploration, analysis, and knowledge dissemination. The objectives of this experiment is to demonstrate the law of conservation of mass and law of definite proportions and to understand the meaning of limiting reagents.
The oral report focuses on two essential scientific principles, the law of conservation and the law of definite proportions. These principles have revolutionized our understanding of the physical world, are the foundation of chemistry. The law of conservation, introduced by Anton Lavoisier in the 18th century, states that in a closed system, the total mass of substance remains constant despite changes they undergo. This law explains that matter is neither created nor destroyed, but it transforms from one form to another. This idea has paved the way for precise explanations of chemical reactions and advancement in various scientific fields. In simple terms, the law of conservation means you can create something from nothing or make disappear entirely. Matter stays the same, just changing its forms. The law of definite proportions, complementing the law of conservation, states the compounds always have the same element in fixed mass ratios, regardless of their source of method of creations. This was crucial, establishing the atomic theory, which explains that matter is made of invisible particles called atoms, combining in specific creations to form compounds. For instance, water always has two hydrogen atoms for every oxygen atom. Regardless of its origin, this consistent composition showcases its precise arrangement of particles. These laws are interconnected. The law of conservation explains how matter transforms, while the law of different proportions unveils the compositions of matter of the atomic level. In conclusion, these laws are foundational to science, bringing the gap between the observable world and the microscopic realm. This inspired wonder and explorations, making us active participants in an ongoing journey of discovery.
The next one is the limiting reagents. So limiting reagents are the substances that are completely consumed in the completion of the chemical reactions. So they are also referred to as limiting agents or the limiting reactants. According to the stoichiometry of chemical reactions, a fixed amount of reactants is required for the completion of the reaction.
The observation described involves a series of experimental steps to aim to investigate the law of conservation of the mass. These fundamental principles state that in any closed system, the total mass of substance before and after chemical reaction remains constant. These experiments provide a hand-on approach to validate this law through the manipulation of reactants and to measure of the mass change. This initial setup have three test tube contains specific amount of sodium carbonate solution, calcium chloride solution, and dilute sulfuric acid are placed with a large beaker. The beaker and its contents are then weighed to establish an initial mass measurement. In the subsequent step, different reactions are triggered by the combining the reactants in various ways. First, the calcium chloride solution is mixed with the sodium carbonate solution, leading to observable changes.
This mixture likely results in the formation of precipitates or changes in color, indicating a chemical reaction. The test tubes are then reweighed to determine if there's any discernible change in the mass after reaction has taken place. Next, the sulfuric acid. The sulfuric acid is added carefully to the other substances in the first test tube. This addition is expected to induce a chemical reaction as well, which may involve effervescence, color changes, or temperature variations. Then, after the reaction subsides and the test tubes return to the room temperature, their mass is measured once more. Throughout this experiment, the mass measurements before and after each reaction are being tracked. Any noticeable variation in the mass after the reaction are compared with the initial measurements to confirm whether the law of conservation of mass holds true. If the mass remains unchanged despite the chemical transformations, it will validate the law. In summary of this experiment demonstrates the fundamental concepts that matter cannot be created or destroyed but can only change form. And by meticulously tracking the mass changes before and after chemical reactions, the experiment aims to provide concrete evidence of the law of conservation of mass, affirming its role as a cornerstone principle in the field of chemistry.
By manipulating quantities of reactants and observing the resulting precipitates and supernatant liquids, the experiment seeks to provide insights into the consistent composition of compounds. In the initial step, 5 test tubes of similar diameters are prepared, each containing 5 ml of 0.5 mole of barium chloride solution. This solution serves as a constant reactant against which varying quantities of copper sulfate will be tested. Subsequently, different amounts of 0.5 mole of copper sulfate solution are added consecutively to each test tube, with quantities ranging from 1 ml to 5 ml. This addition includes varying proportions of copper sulfate solution with the barium chloride solution, potentially resulting in the formation of a precipitate. The experiment aims to examine how these different proportions affect the composition and characteristics of the precipitate formed. After adding the copper sulfate solution, the mixtures are left undisturbed to allow the precipitates to settle. This settling process is crucial for the accurate measurement of the height of the precipitate in each test tube.
The precipitate height measurements serve as an indicator of the extent of chemical reactions that occurred. In addition to measuring the precipitate heights, the color of supernatant liquid, the clear liquid above the precipitate, is also observed. So this step is essential as color changes can provide insights into the nature of the reactions and the types of compounds formed. So different proportions of reactants would lead to the variations in color, indicating the varying compositions of the supernatant liquid. So through these observations, the experiment seeks to validate the law of definite proportions. If the precipitates in each test tube have consistent heights and supernatant liquid exhibit the same color, it will confirm that the proportion of elements in the compounds are fixed and unchanging. This this outcome will align with the principles of the law of definite proportions, demonstrating how the experiments of substantiate the key of chemical theory. So in conclusion, this experiment provide a tangible demonstration of the law of definite proportions, systematically varying reactant quantities and observing resulting precipitates and supernatant liquid. By conducting this observation and measurement, the experiment contributes to our understanding of how compounds maintaining consistent compositions regardless of quantities or methods of preparations used.
The law of conservations of mass. Total weight before first mixing. No chemical reactions. Their liquid color. Weight in grams is 167.4 grams. In total weight after first mixing, they have gel-like features. Total weight is 167.2 grams. It loses 0.2 grams of weight in second mixing. Third, total weight after second mixing, bubbles reactions comprise the white particles. Total weight is 167.9 grams. The white liquid go into the bottom of the test tube. When the reaction finishes, the white particles sink down, have white solid color, and the upper part of mixture have clear liquid solution.
For the calculations in difference in weight before and after mixing, so the weight before mixing, so the two chemicals is 167.49 grams. After moving the two chemicals, so its weight decreased an amount of 0.2 grams, resulting the total weight of 167.29. So the difference in weight after mixing and second mixing, so the weight after first mixing is 167.2 grams, and when we conducted the second mixing, the weight of the mixtures decreased to 167.9 grams.
In question number 1, what happened when the sodium carbonate solution mixed with the calcium chloride? The answer is when the solution sodium carbonate is mixed with the solution of calcium chloride, we have a double displacement reaction. The ion in the two solutions switch partner from the new compounds. In this case, the calcium carbonate precipitates out of the solution as a solid, while the sodium chloride remains dissolved.
Question number 2. What are the indications that a chemical reaction is taking place in procedure 1 to C? So mixing these compounds initiates a series of chemical reactions. Sulfuric acid reacts with sodium carbonate to yield a sodium sulfate and release a carbon dioxide gas. Subsequently, calcium chloride interacts with the produce of sodium sulfate, resulting in sodium calcium sulfate formation. So while sodium chloride remains dissolved. So indication of these reactions involve the effervescence due to carbon dioxide release from the sulfuric acid sodium carbonate reactions. So a white calcium sulfate precipitate forms as calcium chloride, reacts with the sodium sulfate, possibly causing a temperature change to exothermic reactions.
Question number 4. What is the reaction when barium chloride and copper sulfate are mixed? Barium chloride plus copper sulfate is equal to barium sulfate plus copper chloride. The resulting barium sulfate from the reaction has low solubility in water, causing it to form a solid precipitate that is frequently observed as a white sediment. Number 5 question. Are there differences in the amounts of precipitate formed? Why or why not? Yes. There are differences in the amounts of the precipitate that is formed in the bottom of every test tubes because of the reason that we poured different amount of copper sulfate in every test tubes with barium chloride.
For question number 6, why are there color difference at the test tube? The variation in color when adding different amounts of copper sulfate to barium chloride solution arises from the creation of diverse complex ions and compounds during their reaction. The products formed, including precipitates and complex ions, can display distinct colors. The specific colors witnessed depend on the reactions and compounds formed, influenced by reaction proportions and reactant concentrations. Different compounds and complex ions